Hi, my name is Cole, and my project focused on the control of coupled mode systems. Coupled mode systems refer to systems of oscillators that have weak coupling between them. A basic example is a set of two spring mass systems coupled by a weak spring in between them. Other examples include optical resonators or qubit systems. My approach to controlling these systems was to use the affine linear parameter varying control. LPV control takes advantage of the affine nature of the nonlinearity in the system. The idea is you find a K matrix similar to linear control, only this K matrix depends affinely on the state variables of the system. And we can use semi-definite programming to find the parameter varying K. The idea behind the program is we set up a bounding box for the maximum absolute value of the state variables and their derivatives, and then we find a P, the opposite of matrix, and K, such that the following matrix is positive semi-definite at all the vertices of the hyperrectangle. F is a simple but is a large but linear function of p and x dot. Note that the dependence on the derivative is crucial. It's not enough to certify stability to each possible b. You need to take into account the derivative, and I'll showcase this later. Since Drake doesn't natively support LPV control, I implemented the program in YALMIP using Mosaic semi-definite programming solver. And I focused on a single resonator in a set of coupled mode systems for visualizing the results. And we can get to the results. Now, the first result isn't all that interesting. It's a simple exponential approach, but the plot on the right, I think, really shows the power of the controller. What we see is that the controller, starting from 0, 0, finds its way to the natural curve of the resonator, so it can ride its way up to the target at point 8.8. Similar to what happens in swing up control of the pendulum, which is this is a very surprising, not intuitive, but very clever approach the controller takes. Next, I wanted to demonstrate what happens if you try and drive the system outside of its bounding box. And this is what happens if you try and drive a derivative that's too high. The controller goes crazy and starts trying to drive the system to infinity. And what's interesting is this instability is coming from the controller. The system natively is stable at 0 without input. So it's the controller causing this instability. Finally, I wanted to get what I thought were the coolest results from this project. What's happening here is we online switch the target that the controller is trying to track. So we see the controller swing up to the first target, and then we change the target, and it's able to swing up to the next target. So LPV control was very powerful. It allowed computation of the controller once offline that could be used forever. It certified stability and reachability within a bounding box, and it performed highly non-intuitive maneuvers, reminiscent to swinging up the pendulum. And overall, I just thought it was really cool and had amazing results.